So what happens if we have the same factor more than once? How do we handle a repeated root? Something like this here, where we have 1 minus x over x squared. Where, if you want to think about factoring that out, well, you could factor out that x squared. You would get something like 1 minus x over x squared is equal to 1 minus x over x multiplied by x, which, if you think in terms of these as being separate for that kind of thing, you would have a over x plus b over x is equal to a plus b over x, which is just c over x. No, that doesn't work. It doesn't add up at all, because that would imply that something in here cancels. No, this is not. This is very much not good. So much not good that I'm actually just going to erase this, which is a bit unusual for my videos. But hey, don't even think about that. The problem there is that in trying to factor out the x, we end up getting something that's kind of trivial with that repetition. It doesn't quite clean up nicely. So let's think a little bit more generally here. Let's think about something like 1 over x minus a squared. So there, a is 0. And with a thing like this, and 1 is not just 1, but don't worry about that. What we want to do here is take the thing of the next power down. So we want to take the thing that's the next one down from a square. Well, excuse me, that shouldn't be a 2. It's still just an a squared. If we've got a square, we've got a degree 2. The next thing down from degree 2 is degree 1. We want to describe any potential degree 1 thing. We need an x term, a single x term, plus the potential for constant terms. We need a general linear thing, ax plus b. Okay, so you've got ax plus b over x minus a squared, and somehow the ax plus b is going to end up being 1? Well, what we can do there is split this up a little bit further. We're going to use a trick that most people don't really like. We're going to add 0. But we're going to add 0 in a really special way. Because what I'm going to do is I'm going to take this ax, and I'm going to subtract from it a small a times big A, which looks really, really dumb, I know, but there's a reason why I'm doing this. And this here, it's just a number. It's two numbers that we don't know for sure multiplied together, but that's still just a number. But because I subtracted that, excuse me, I also have to add it. And then we have this really stupid thing over here. That's an AA plus a B. And then down here we still have x minus a squared. But I'm going to split this up. And I'm going to have ax minus AA over x minus a squared plus AA plus b over x minus a squared. And then right here, I'm going to recognize that if I factored out an a, I would have a times x minus a over x minus a squared. And then over here, I'm going to recognize that AA is a constant, B is a constant, take a constant times a constant, still have a constant, add a constant, still have a constant. So I'm going to save myself a little bit of notation and just call that C. So C over x minus a squared here, I have an x minus a and another x minus a. These cancel, and this turns into a over x minus a, no longer squared. So I shouldn't even need those parentheses anymore, because those aren't really necessary without an exponent, plus some other constant c over x minus a squared, where, just to be sure, make that a big C, is equal to small a times a plus b. It's just a re-representation of our constant to save a little bit of notation there. But the point is here, if we have repeated linear factors, if you have something more generally of form px over ax plus b raised to the power n, then that just splits out into constant terms for every power of n. So we'd have a1 over ax plus b, a2 over ax plus b squared, a3 over ax plus b cubed, and so on down the line until we get to an ax plus b to the n. We always just take one down from whatever our factor is without any repeats thrown in there. And we just split it up in that way. So if you want to work on this example here, I might not have enough space to do this one, but actually I might because it's pretty small. So if we took 1 minus x over x squared, we would end up having a over x plus b over x squared. We get a term for every repeat with the next one up in terms of the smallest, so these are all just constants there, which would then become 1 minus x equals ax plus b, and technically speaking, you could write that as a system. You should plug in some values to solve it, but hopefully you can tell that looking at this, hey, that means a has to be -1 and b has to be 1. So if you want to write this out, to split this up, you actually don't really have to do anything. It's really just -1 over x plus 1 over x squared. Because, you can just split up the top and there's nothing really interesting going on in the bottom. So that's not really a very good example. So I wrote out a lot of steps here. We've got a whole lot of things going on here with some very general constants. Like I said, when you have these very general things, it's easy to lose track of what it is we're trying to do with a thing like this. So let's get a more concrete example here to finish ourselves off on this process for linear factors before talking about some maybe more general things.